All right, only 2 reminders about today. Well, your project's due. Make sure you submit in time, but we'll finish early today, so hopefully you can still grab some time for some last minute tweak. The review session will be 1 p.m. This Thursday. That's kind of the only time I can really make it to the campus. Try your best. If we got enough people there, I'll definitely hold it and definitely record it so you can still take advantage. Try to be there so you can ask your own question, but we'll see how that goes. If too few people show up, I might just turn that into office hour so you guys can still ask me question in person. All right. So today, I just want to finish the final bits about the bottom-up parsing and then finish off by introducing 2 terms, which you might actually hear later whenever you hear about ambiguities, about bottom-up parsing. Let's do that one by one. All right, that's the Goto algorithm, which we did last time. Okay? And there's one example I want to do just to wrap up. It's more like a new example. And I just want to point out to you guys over here. When we talk about the Goto algorithm last time, over here is a symbol X. Okay? So I kind of based the algorithm over here on some textbook. So here, when they say symbol, okay, as we will see later, don't be too restrictive. The symbol here, what I gave you the impression about it last time was it's only just a terminal. However, terminal definitely works. It can also be a non-terminal, like a variable. So I want to do another example with you guys, just to make sure you understand both. So X over here can be either a terminal, and the example we did last time was just over here. Let me show to you. The example we did was just a opening parenthesis. That's one case. Another case, which I'm going to go over with you. Oh, there was a little typo here. Over here, that should be a list. Okay. Another possibility would be it could be also a non-terminal, like a variable. When you eventually build the transition table for the parser, for the Goto table, for the action table, it's actually going to take either a terminal or a variable, right? That's something you will see. All right. So later on, when you review this example here, I'm going to go a little bit quickly because that's something we did last time. But I'll definitely highlight to you what you should really watch out for. Let's look at the question first. You want to calculate the following input on the Goto. We have some starting LR1 item set, which is this one here. And remember, this is CC0 is what we calculated last time by using closure, right? Just make sure you review that. So this will be the starting input, and then it is reading rather than just a terminal. It's now reading a variable. This is what it is saying. If currently I'm now in the set, the subset states CC0, and then somehow for parsing I can read the whole list like a variable, maybe by reduction. In that way, where should I go to in the next stage? That's what it is calculating. So this transition over here in the context of bottom-up parsing, this can be a variable or it can be a symbol, like an opening parenthesis, like what we said last time. All right? And that's the problem we have. All right? We want to calculate this. And the procedure that we're going to follow will be just the same as last time. So let me do a little bit more quickly, just to show you what you really watch out for. Okay, number one, we want to look at the input set over here. And since we are trying to read the list, so that means we want to find out the X. So this X over here is going to be replaced by just the list. Over here, the X will be replaced by just the list. We want to find out every item in the input set where the bullet point occurs just before the list. And then we're going to create some new item where we're going to shift the list right after. Okay, sorry, let me say it again. The input there, we're going to find out all the bullet points that appear before the list, meaning that we haven't recognized that yet. And we're going to create some new item over there by putting the bullet point after the list, indicating we have already recognized it. Okay, that'll be the procedure. Let's do this one first. That one's easy. Right, let's look at the input over here. Okay, guys, quick exercise for you on your eyes, right? How many items can you identify for this part here, where the bullet point goes right before the list? How many? Just tell me how many. 3. Okay, William told us 3. Hopefully you guys agree. Very good. Okay, it's exactly one here. Oh, sorry, too thick. One here, and one here. So these 3 input items will definitely trigger some additional items. Level 1. They are going to trigger the following 3, which I'm going to highlight in the output. So CC1 over here is the output that we're going to generate eventually by this Goto. This will be 1, and this will be 1, and this will be 1. Okay, let's see the one-to-one correspondence. You can see here, for this item here, they are green. The additional item here, they are in the blue, right? So let's take a look. Let's say this one, for example, you can see the bullet point is before the list. And for this one here, the bullet point is after the list, right? You can see the correspondence over here. And similarly, for this one here, bullet point before the list. For this one here, bullet point after the list, and etc. So these are the 3 additional items. Are we okay with this step over here? This step here is pretty straightforward, right? Okay, and then that's the only 3. But we have to make sure after we have calculated the moved, so the moved over here upon this point, we only got 1, 2, and 3 items. But we need to calculate its closure, all right? The closure part, okay? Let me give you guys some little hints. You can think about after calculating the closure, we're going to get 1, 2, 3, and 4. 4 additional items, okay? But let's see a little bit more closely why. So this might be a nice review about how to calculate closure. So for example, so what we want to do is we want to calculate the closure of the set containing this one here. The goal produces the list, bullet point, EOF, and also this one here. It would be the list produces the list pair, and then EOF. Okay, there's a comma here that's missing. And the third one is over here. It would be the list produces the list, bullet point, pair, this, and opening parenthesis, right? We got 1, 2, and 3. And we want to calculate about their closure, right? Just to be a little bit more consistent with the color, I'm going to turn them into blue. Right? You can see these ones are passed to the closure. Now, what will be the closure? Well, I'm going to let you study the algorithm more closely. I'm pretty sure you do that for the exam. Basically, you have to look to see what can go after the bullet point. Okay? So, just notice that there's a comma here. Okay? You can see after the bullet point over here, before the comma, there's epsilon over here for the first case. For the second case, you got a pair, right? Between the bullet point and the comma. Here, between the bullet point and the comma, you also got pair, right? So that means we have to look into the rules for pair, okay? And what are the rules for pair? You can see we got over here, the rules for pair will be this one here and this one here. So that means we need to, this will be dimension number 1. So dimension number 1, we got 2 alternative for pair. So we got pair produces pair, and also we got pair produces this, right? That's the first dimension. And what's the second dimension? For the second dimension, we have to worry about the first of the delta A. That's from the algorithm, all right? In this case, I'll let you calculate it in detail. But in this case, what would they be? Well, take a look. Let's say in this case, we got pair over here, we got pair over here. One is followed by EOF. You can see one is followed by EOF, the other one is followed by this. So these are the 2 you're going to collect, okay? I'll let you study that algorithm more closely. So that's why eventually what you will get is, you're going to get, for example, this one here is corresponding to this. The bullet point appear right in the beginning, and then you got EOF. You got another alternative, which will be the bullet points still appear before that, but you got opening parentheses. Right? These are the 2. And then for these 2 over here is corresponding to this particular alternative. Bullet point in the beginning, and what about the look ahead symbol? Either opening parenthesis or EOF. Okay? So dimension number 2 is something you can easily calculate using the steps that we talked about last time. So that will be the first of delta A. Okay? So this is something you can also see. All right, guys, I'm deliberately omitting some details over here because that's something you have to do the pattern matching like last time and then calculate it. Okay? Are we okay about this? So this first example here, number 1, it reviews about how we can calculate the Goto. And also number 2, it tells you that whenever you're trying to use the Goto over here, the input can either be a terminal, which we did last time, or it could be a variable like what we just did, either way. Okay, so this will be very useful for calculating the transition table in just a moment. Okay. Any question about this example here? All right. All right, very good. Let's now move on quickly. And we got 2 more small algorithms, but both of them are straightforward, okay, to actually go over. So if you go back to the slides after the Goto, so the first algorithm to go to is to build the canonical collection over here. Okay. Let's now go over the algorithm line by line, and then we wouldn't need to trace this one in detail. I'll just show you what the outputs are. I'll suggest some exercises for you. Okay, let's take a look. Okay, this one. The input is going to be some grammar, and there will be some Go production. You can think about the S over here is simply just the start variable, typically. Okay, so this will be the start variable. If the grammar is actually, let's say this is the example grammar, so this will be the Go production. Okay, because Go produces lists. Eventually you want to get a list. And then the output will be 2 things. Okay, we're going to look at the output in just a moment. We're going to calculate all the reachable subset states, right? CC0, starting with that, see what are reachable from CC0 by using the various Goto. And then we also want to, at the same time, build some transition function, and we'll see how that would look like. Okay, let's now take a look. Okay, CC0 is exactly how we calculate it. You can think about the star variable over here, and then EOF, right? That's what we did before. I think there could be some typo over here I should fix. Okay, I think this is S, this is S prime. Okay, I'm going to fix that also on your slides. So that will be the closure of the initial states of the parser, and then we start with the CC just being CC0. We're going to keep growing this set until we have nothing that allows us to grow. Okay, let's see how to do that. The way to do that is for every iteration, you're actually going to look for the bullet points. So look for, so this means we are ready to recognize a terminal or variable. And we just use the variable or terminal, just use X. That's the symbol. So the X over here is not necessarily just a terminal. It could be a variable as well. So we just want to find out in the CC set so far, and then we want to find out all the items where we can simply just ready to recognize another thing. Okay. Once we find that, we can just say, we can just go to that particular set. Okay. So this is to say, let me just take a look at this. So this here is to say, make a transition from CCI, which is the current set, via recognizing X. So let me just visualize that a little bit. You can think about if the current set is actually CCI, and we want to know what the target state is if we try to take a transition by recognizing X. And X can either be a variable or it can be a terminal. That's basically what this is doing. We'll keep doing this and then keep growing the CC set until we cannot go any further. Okay? And then at the same time, we can also update the transition function. The transition function basically is going to be a source some symbol and target. Okay, we'll show you the example right away. Okay, you can think about this is a source states, and this one over here is the target states, and this one over here is the transition that we can take. So this algorithm over here, we can actually get two outputs. One is all the reachable sets in a canonical collection. Number two is the transition function. Okay, and we don't really have to execute this algorithm entirely. Too tedious. We don't need to. However, what can I ask you in the exam? What I can ask you about is, I might give you a particular, let's say, item over here. And I would say, given this item here, how can you calculate the corresponding, for example, this? And what can be the corresponding entry that we have to add into the transition function, and etc. I wouldn't ask you to really show the tracing for the entire algorithm. I'll just ask you to show some steps. Okay? All right, let's now take a look at the output very quickly. Output number one. For this particular grammar over here, this grammar here, so these are all the canonical items over here. Right? We showed you very briefly last time. Right? So far we have seen three already. This is CC0, the initial one. Okay, we knew how to calculate it from last time. CC1 is by taking a transition. CC1 is by taking a transition of the list variable. And CC3 is what we calculated last time by taking the transition of opening parentheses, okay, using Goto. And for others, right, just by different transition. Okay, to be more visual, this will be the corresponding transition diagram. How do we read it? So let's say this. Initially, we are in CC0, subset states. By taking the list, we can go to CC1, which we just calculated today, right in the beginning. And also, you can, starting from CC0, you can also go to, you can go to CC3 if you take this. That's what we did last Wednesday. So far, these two have been covered. In the exam, I can say, I'll give you one state over here, and then I can potentially give you another state and ask you, how is these two states related? That's one way to ask. Or I'll give you this and say, taking this transition here, what will be the corresponding subset states? You just need to show me the computation. Okay? And just one more thing. There's another way to visualize this, this diagram, which we definitely talked about back in the DFA lecture. So I'll just show you one row. Let's say the starting state is CC0. By taking, for example, the list variable, the corresponding target state should be CC1. How can you see that? So CC0 over here, starting from that, taking the list over here, and you get to CC1. That's how you look it up. And if you say in CC0, you take the goal, undefined. Okay? So it's not defined. So that's why you simply put empty set. Because every entry there is a subset states. If that's undefined, just empty set. Guys, are we okay so far? You can think about the go-to there is really how we built the transition gradually. Eventually, that's what we will get. And you might just be asked about how a particular entry should be calculated in the exam. That's what you might be asked. Okay? Any question about this? Okay, that's the first algorithm. And there is a final algorithm that we have to go over, the final one. And if you look at this table here, okay, this table is actually what we actually assumed about maybe 3 or 4 lectures ago. Let me remind you very quickly, if I can find it very quickly. Maybe about, right here. Okay. If you remember the tracing we did about bottom-up parsing, right? I said, let's assume there's such a table. And after that tracing, we actually have been talking about, LR1 item, canonical collection, etc. Now we should know how to build this table from scratch so that the bottom-up parsing algorithm will really work. So it's exactly over here, bottom-up parsing. Okay. Let's now go back. Okay, let's now go back over here. Let's take a look. And the each line here it actually is very logical. Let's look at the input and output quickly. Input will be a grammar, for sure. And also a Go production, the star variable 2 produces whatever it is expecting. And also we're assuming that these two are already available to us. Okay, so I'll make a note over here for you. These two are presumably calculated by BuildCC that we just went over here. Okay, produced by Build the canonical collection. Okay, and what will be the output? The output will be action table and go to table, and this will be the output right over here. Okay, right over here. To be honest with you, after we have got this particular transition function, filling up this table here is very easy, very straightforward. Let's just go over some quick example, and then you will see the point. We're just going to run some loop, and then we have to know when to fill in the shift, when to fill in the reduce, and when to fill in the accept, and etc. Okay? Let's take a look at 3 examples. Okay? Example number 1. How do we fill in the shift action over here? So this is to say, let's say this. You have, okay, when you need to fill in the shift operation over here, there should be a corresponding transition going from CCI to CCJ. I and J here are the state number. For example, you can see here, we actually got, let's see here, this one here, and this one here. Okay, so if we are now in CC3, by taking this, we will actually go to CC6, right? If you look at that. That one there is like a delta of CC3 by taking opening parenthesis is going to give us CC6. So now if you look at the 3 and 6 over here. So that means correspondingly you have to fill in the action table, right? So here should be 3, and here should be 6. That's exactly what you will see here, 3 and shift 6. All right? Of course, you should really look at it more closely. I'm just trying to highlight right away to you how you can fill it in. Don't lose the big picture. What we're given is this particular transition function, given that we will be able to fill in the entries in the table one by one. Okay? Let's look at another one about reduce. Very similar. For the reduce, you can look at the condition here. Whenever we got some item where you can see the bullet point is already at the end of the production rule. That means we are ready to read the look ahead symbol and then reduce. Okay? And one example would be, let's look at this one here. Let's say here and here. Okay? So if you look at CC8, this one over here is already the accepting states, CC8. So here that means we don't have to read anything over here. So let me just fill it in for you. So if you look at the CC8, CC8 is already an accepting states, meaning reading EOF will reduce. All right? Okay, that's the second one to see. Okay? Are we okay so far? Okay. So this one here, let me see. I think these are the examples I want to go over with you. Just make sure, you have to make sure, if I give you this transition function here, and then I may ask you, based on this transition function, how can you fill in some particular entry in the table? That's something you will have to make sure you know how to do. Okay? Are we okay with this? Or you want to maybe take some time to look at this before Thursday? We can definitely revisit this. So here I'm just highlighting what you should really watch out for when you study the algorithm. Okay? Maybe take a look at this. If you do have question here, we can revisit again. But you definitely need to take some time. But the critical thing is you want to really match the pattern over here If you match the first one, you're going to fill in some entry for the shift. If you match the second one, you're going to fill in entry for reduce. If you match the third one, you're going to fill in for accept. For example, like over here. Okay? And this part over here is just for filling in the Goto table. Okay? But it's also based on the delta function as well. For example, you can see from CC6, by taking pair, we're going to CC9, exactly over here. Okay? Similar. Okay? Let me make a note over here. So this part over here is for filled in the Goto table. Okay? So the final bits that we really have been talking about so far is just by using the Goto function and also the closure that actually we spoke about last time. And make sure you just know how to combine them together. The ultimate output is to produce this table over here and also this table over here. All right? Okay, any question about this? We okay? Okay, take some time to make sure you're okay with this. All right, so that's about this part over here. And if you look at the slides, there is another example. Oh, that's the algorithm that we just went through. Okay? And you will see that there is actually one more new grammar. So this is just another grammar here, and similar exercise as before. How do you calculate the CC? But I would suggest at least try CC0, right? By applying the steps that we talked about before. At least try CC0. And then you can calculate transition function. Try a few entries. And you actually see that this is the ultimate transition table. Again, you don't need to do the whole thing. What you need to do is maybe randomly pick some entries from there and try to do the corresponding calculation. Verify yourself. Okay? That would be my suggestion. Okay? Don't do the whole thing. You don't have the time to do it before Saturday. Right? So this is all the CC that you can definitely compare your answer against. It turns out it has larger parser states. CC0 all the way out to CC13, so 14 states as opposed to what we had before. Okay? Just a different parser. All right? All right, the final slide and the final point to make is about what kind of ambiguity can you run into for the parser. Okay? And there are two kinds of ambiguity that we can talk about. I'll put them here. Okay? That'll be the final page to discuss. Okay? Now, I want you to take a look at this particular states. Think about this is certain states for the parser. Okay? Certain states of the parser. Okay? I'm going to describe to you based on our understanding. You guys can think about if there's anything that might go wrong or ambiguous with it and why. The bullet point, well, first of all, the set over here contains two possible items, right? One item here is saying as follows. We have already read this so far. If the next the look-ahead symbol is either this or this, if the next word to match will be either EOF or else, we will be able to reduce back to a statement. Okay, that's what this item is saying. What about this item here? This item is saying the following. We have already read this one so far. If the next one is going to match this one here, we're going to move the bullet point to here by doing a shift. All right? Based on what I have just described, do you see any potential ambiguity? Since these two items are in the same states, right? Is it possible to say the input is something, but it can result in maybe two possible actions which cannot be fulfilled simultaneously? Is it possible? Anyone? So here, by reading EOF or else, right? Either this or this. We can reduce to the statement. That's the first one. All right? We agree with that. That's by the very definition. What about this one over here? This one is by reading else. Here we don't really look at the lookahead symbol just yet. We only look at the lookahead symbol if we are at the end of the production, okay, the recognition. By reading else, we shift to exactly over here, okay? The bullet point. Right? Are these two actions consistent? Not really, right? One is about shift. The other one is about reduce. One is to say, I can shift the bullet point to here. The other one is to say, I want to reduce to the statement. There's a conflict. Okay? So this is either shift or reduce to the statements. So this is the so-called shift-reduce conflict. And I'm not too sure if you guys encountered that when you actually design your grammar in Untitled 4. Some ambiguity actually belong to this category. Okay? And one thing to say, what should be done in practice? In practice, having the shift-reduce conflict is not really fatal, meaning that you don't necessarily have to fix your grammar. The compiler or the parser generator like Untitled 4, they normally take the shift as default action by resolving the ambiguity for you. Okay? But you should know that theoretically it's an ambiguity. But in practice, the parser generator might just generate a parser in a way it's going to do the shift. Okay? That's some aside for you to know. In practice, the shift will be done. Okay? But in theory, it's an ambiguity. All right? That's the first one. Okay? Shift-reduce conflict. What about the second one? Second one is a bit symbolic. Let's say we got another parser state number I. And then we got these two items. Okay? And somehow, these two items tells us we have already read these two. Okay? So this is to say, these two over here, gamma delta, already recognized. And this is to say, and also they share the common look ahead over here. And this one is to say, by reading A, some reduction should happen. Right? Both of them is telling you, after reading this, if I read another A, I should really reduce to this symbol. For this one, after reading the same thing, I'm now here. By reading another A, I should really reduce to this. Now, are we in a conflict? We are, obviously, because these two variables are different. What if one asks you to reduce to an expression? The other one asks you to reduce to the statement. So that's also a conflict. Okay? And this is the so-called reduce-reduce conflict. And unlike the shift-reduce conflict, in which case, in practice, the parser generator can help you resolve it by choosing the shift. But for the reduce-reduce, it is fatal. That means the parser wouldn't know which one you really meant to reduce into, either A or B. So in this case, if you got reduce-reduce conflict, you must make a choice or by redesigning the grammar. Okay? This one here, that means you must fix the grammar. All right? All right, so these are the two very common ambiguities you might run into if you try to use some parser generator, and then your grammar may contain some ambiguity, either shift-reduce or reduce-reduce. All right. Guys, that's it. All right, about everything. Okay? And do you guys have any questions? All right. So for the exam, I can very briefly talk about it. Okay? So we don't need to take a break. I do have your quiz number 3 over here. I'm going to hand it back. Okay. So I think what's to be done for the course, okay? Of course, you're going to submit your project today, and then we will try to get back to you. We'll definitely get back to you some feedback. I'll reach out to you by e-class. So you guys can definitely, if you want to go over some project feedback with me, before the break may not be possible because it might take me and the TA some time. But if you really want to, reach out to me. I'll be happy to do that next semester, okay, in January. That's fine, okay. And for the exam, let's talk about the exam first. Okay. Number one, no multiple choice. Okay. No multiple choice questions. And we said last time, no data sheets, but I will make sure any algorithm you might need, I'll include them in the appendix. Okay. Algorithms included. Okay, as part of the exam paper. All right, let's see number 3. The format will be similar to your quizzes, meaning that you might be given some problem description over there, you got some answer box. And sometimes you might have some short answer as well. Okay, format similar to the quizzes. And of course, you know that's cumulative. That means everything may be covered. Okay, I would say, in case you plan to study that, I'll save you some time. There is no need for you to study. Sorry, let me take a look. Give me a moment. Let me first of all go to our lecture here. Okay, so there is no need to study the overview. We already covered that pretty well in quiz number 1. I feel comfortable. I don't need to test you again. Only study lexical, syntactical, and remember composite and visitor pattern. Okay? Make sure you do that. Okay? I wouldn't really test you specific details about the assignments, but there might be some stuff which I might put on the paper. I'll give you enough detail on the paper. I might also ask you some related questions. So as long as you guys did the assignment, you should be okay. Also Antler 4, tutorial. Okay. Do you guys have any question? To be honest with you, so far I have been mainly making the exam for 2030. I haven't got a chance to start making this, but I think you can expect maybe evenly distributed questions on the exam. For example, there might be some from the lexical analysis, some from the syntactical analysis, maybe some from composite, some from visitor, etc. Okay. All right. Do you guys got any questions for me for now? Or you can save that for Thursday if you plan to come. All right. We okay? Well, guys, thank you so much for the entire semester. And then I'll see you on Saturday, if not Thursday. And then you can definitely expect me to reach out to you when things are more things are available about your grades. And then, yeah, I'll see you around. All right. Take care.